current voltage feedback. In some circuits it is desirable or simpler to sense the output current to perform feedback. The current is actually sensed by placing a small resistor in series with the output and using the voltage drop across the resistor as the feedback information. This voltage may even serve as the written signal that is directly subtracted from the input. Here you can see the figure current voltage feedback. Let us consider the general current voltage feedback system illustrated in figure. Since this is a feedback network, senses the feedback network senses the output current, and returns a voltage. Its feedback factor beta has the dimension of resistance and is denoted by RF. Note that a finite load ZL is connected to the output so that I out is not equal to 0. We can thus write VF equal to RF I out. IE is equals to V in minus RF I out, and hence I out equal to GM V in minus RF I out. It follows that I out by V in equal to GM by 1 plus GM RF. An ideal feedback network in this case exhibits zero input and output impedances. It is instructive to inform that GMRF is indeed the loop gain as shown in figure. We set the input voltage to 0 and break the loop by disconnecting the feedback network. Figure calculation of loop gain for current voltage feedback from the output and replacing it with a short at the output. If the feedback network is ideal, we then inject the test signal IT producing VF equal to RF IT, and hence I out equal to minus GM RF IT. Thus the loop gain is equal to GM RF, and thus the transconductance of the amplifier is reduced by 1 plus GM RF when the feedback is applied. Thus sensing the current at the output of a feedback system increases the output impedance. Thus is this is because the system attempts to make the output current a faithful replica of the input signal with a proportionality factor if the input is a voltage quantity. Consequently, the system delivers the same current waveform as the load varies, in essence approaching an ideal current source, and hence exhibiting a huge output impedance. To prove the above result, we consider the current voltage feedback topology shown in figure, where R out represents the finite output impedance of the feed forward ampli. Calculation of output resistance of a current voltage feedback amplifier. The feedback network produces a voltage VF proportional to Ix. VF is equal to VF Ix, and the current generated by GM equals minus RF Ix GM. As a result, minus RF Ix GM equal to Ix minus Vx by R out, yielding Vx by Ix equal to R out 1 plus GM 1 plus GM RF, the output impedance therefore increases by a factor of 1 plus GM RF. As a voltage feedback, current voltage feedback increase the input impedance by a factor equal to 1 plus the loop gain. As illustrated in figure, we have Ix Rn GM equal to I out, thus V equal to Vx minus GM Rf Ix In, and Vf Vx by Ix equal to Rn 1 plus GM Rf. Here you can see the figure calculation of input resistance of a current voltage feedback amplifier. The reader can show the loop gain is indeed equal to GMRF. In summary, current voltage feedback increases both the input and the output impedances while decreasing the feed forward transconductance. As placed in chapter, the high output impedance proves useful in high gain op amps. Thank you.